going? Long time no see, at least in YouTube form. Hopefully you guys enjoyed the movie After the Test. Today we're looking at some optimization problems. These are really fun, complex, rich problems that really go after, math as a tool to solve problems. So we'll kind of look at these through examples and see the best way to solve these problems that can be a little bit tricky. Okay, so here's the scenario. We're gonna figure out the process on these by just doing a few problems and seeing the best process. So a farmer wants a rectangular pasture for his animals. The pasture will be bordered on one side by a river, with three sides bordered by fencing. So it's a rectangular pasture, but what's important to take from that sentence is that it's not going to be fenced on all four sides of the rectangle. One of the sides will be a river, and then three on the other side. The farmer has 2,000 feet of fencing to work with. What are the dimensions of the pasture that maximize the area for the animals? And what is that area? Okay, so first off, let's kind of get a sketch of what's going on here. We're putting this pasture in, but it's important to know that there's a river. The river will be one of the sides of the pasture, so we won't need fencing on that side. So let's take a look. So here we have this river. Okay. What we're going to do is we're going to use the river as one of the borders of a rectangle to create this pasture. Now just thinking, since we want the area to be as big as possible, we'd want the river to take up a pretty good stretch of fencing because we don't have to put any fencing there. So my guess is it's going to look something like this. Okay. So here's our rectangular pasture. What we want to do is start labeling things with variables. Well, one thing we know about rectangles is that opposite sides are congruent. So whatever I call the top, I'm going to call the bottom the same thing. So I'm going to use x and x for these two dimensions. They have to, I don't have to choose x, but whatever I choose for the top, it makes sense to choose the same letter for the bottom because I know that they're the same. But rectangles don't have to have all four sides congruent. That's only squares. So I'm going to name this, the third piece of fence here, I'm going to call it y. So the first thing we want to do on these types of problems is we want to kind of sketch a picture here to get an idea of what's going on and start labeling some variables. We always want to eventually get down to one variable. So instead of doing x, y, and z here, I can get down to just two variables by realizing that, a rectangle, the opposite sides have to be congruent. Okay? The length of river there that's bordering would be a length y, but I'm not going to label it y because what I'm concerned about here is the amount of fence. So there's no fence on the river, right? The animals just, maybe they can't swim or something. They'll stay in the pasture right there. Okay. So the first question you have to ask yourself is, what is being optimized? Now the word optimized, right, means the best possible scenario. It could be a maximum, it could be a minimum, okay? So in this case, our optimization is a maximum, and we want to maximize the amount of area for the animals. So we want to maximize the area of that rectangle. So what's being optimized here is the area. So my area of this rectangle is what's being optimized. So here's what I just want you to think about it. If we made x really, really tiny, y would be really big, but it would have a really small area, right? Imagine x being 0. Well, then the area would be x times y. 0 times 2,000 would still be 0. Okay? If I made x really big, right, If I made x 1,000, then I'd have 1,000 feet on that top part, right? This would be 1,000, this would be 1,000, and y would be 0. There wouldn't be any length to that rectangle. So again, my area would be 0. So the answer is somewhere between 0 and 1,000. X is going to make the maximum area. Okay? So what you want to do is you want to figure out what's being optimized. In this case, it's area. And then you want to write an equation for area. Well, the area of this pasture will be xy. And what I want to do then, if I graphed the area, right, I know that if this is x and this is the area, I know if x is 0, my area will be 0. I know if x is 1,000, my area will be 0. Somewhere in here is a maximum value for x that's going to create the biggest possible area on there. Okay? That's what I'm trying to find. Now, you may have looked at problems like this in Algebra 2 or Pre-Calc, and you just graphed it and found the maximum on your calculator. Well, we're going to do it using calculus. So what I want to do is I want to figure out, just intuitively, how do I find a max or a min? Well, maxes or mins are always critical points, and critical points are when the derivative of the function equals 0. So what I want to do is I want to take the derivative of a and set it equal to 0 and solve for either x or y. The problem is here I have two different variables, x and y. What you always want to do in these type of problems is you want to get it down to a single variable. So I just want area in terms of x or area in terms of y. Well, I can't do that right now unless I consider the constraint. So your constraint is what's limiting you, or what's being forced upon you. So our constraint here came up right here. We only have 2,000 feet of fencing. So our constraint is that we only have 2,000 feet of fence to work with. What I want to do is I want to write an equation from my constraint, and then I want to use substitution to be able to solve this, to get this area equation down to a single variable. So here's the constraint. The constraint is I only have 2,000 feet of fence. Well, 2,000 would represent the total amount of fence. It's not quite the perimeter of this rectangle because there's no fencing on the river side. So here's what I know. The perimeter of these three sides has to be 2,000. So I can write an equation that says 2,000 equals 2x plus y. And I know that this has to be true. Whatever I choose for my dimensions, x plus y, or 2x plus y must equal 2,000 because I only have 2,000 feet of fence. I can't have a big hole in the fence or the animals are going to escape. So what I want to do now is I want to substitute, I want to solve this constraint for either x or y, and then sub out x or y in my equation. Now, sometimes it doesn't matter. Sometimes there's definitely an easier way to do it. So when I look at my area equation, I just have x times y. So neither one is particularly more difficult to sub for there. When I look at my constraint, I see that it's going to be easier for me to solve the constraint for y than it will be to solve for x. Because if I solve for x, I'm going to have to divide by 2, and I'm going to get a fraction. And, you know, given the choice between using a fraction and not using a fraction, I would prefer to not use a fraction. But if you solve for x, it'll still work, I promise. Okay, so here's what we need to do. I'm going to solve that constraint for y. So how do I solve this equation to say y equals? Well, all I have to do is subtract 2x. And I know that y equals 2,000 minus 2x. Okay? What I'm going to do now is I'm going to sub this 2,000 minus 2x I'm going to sub it in for y in my equation up here. So I can get an area equation that's solely in terms of one variable. So here's what I get. Area equals x times, and instead of y, I'm going to do 2,000 minus 2x. Okay. I don't think the solving of these problems is very difficult. I think it's the setup that makes this really a challenge. Okay. So now I have my area equation in terms of x. And again, because I want to find a max, I want to do the derivative of this and set it equal to 0. Now I can do the derivative right now and have to do a product rule. But I think this is going to be a little bit easier to do if I distribute that x and just make it into a more simple derivative to do. So I'm going to distribute this x, and I'm going to get my area then equals 2,000 x minus 2x squared. Okay. So that's what the area has to be, and now it's solely in terms of x. So first step, figure out what's being optimized, write an equation. Second step, use the constraint to get it down to a single variable. That's what we just did. Third step, we want to do the derivative and set it equal to 0. Now, these aren't like related rate problems. I don't have to do dx dt or anything like that. The fence isn't moving. The fence is static. I'm just trying to figure out what the max area can be and what dimensions get me at. So doing the derivative here, the derivative of 2,000x is 2,000 minus the derivative of 2x squared is 4x. Okay. So that's my derivative. It's a pretty simple derivative to do there. And what I want to do now is set this equal to 0 and solve for x. Well, once again, this is a pretty easy equation to solve. We get 2,000 equals 4x. And then I divide by 4. 2,000 divided by 4 would be 500. And I found one of the dimensions that I need. It came out to a very nice number of 500. But notice, I said, what are the dimensions, plural, of the pasture that maximize the area? I got one of the dimensions. I've got 500 for x. Okay. I need the second dimension here. And again, I can go back to my equation right here. And I know that y equals 2,000 minus 2x. And I know x equals 500. So y equals 2,000 minus 2x. But again, x is 500. 2,000 minus 1,000 is equal to 1,000. Okay, and go ahead and throw the unit in here. I think we were dealing with feet. Feet. So those are my dimensions. You might want to do a double check here to make sure it all makes sense. Well, I should have 2,000 feet of fencing, which I do. 500 plus 500 is 1,000, plus 1,000 is 2,000. Okay, so that makes sense. Looks like that should be a pretty good area. The last thing I want to do is figure out what the area actually is. I want to know what is that area. I want to fully answer this question. So again, I can either use my area equation right here, since I have both x and y, or I could use my area equation right here if I only want to do it in terms of x. I think it'll be easier to do this one is x times y. So the area will be x, 500, times y, 1,000. 500 times 1,000 is a 5, followed by 1, 2, 3, 4, 5 zeros. 3, 4. It would be 500,000 square feet would be my area. So again, these are pretty rich problems, can be difficult problems, but kind of fun ones too, real life application, right? Things that you could, a business could hire you to figure out. Okay, let's look at the next problem. So it says a rectangular box is being created from cardboard. the box must have a base length twice its width and have a volume of 1,000 cubic inches. What dimensions minimize the amount of cardboard used to make the box? How much cardboard was used? Okay, so again, the first thing here, I like to kind of get a sketch of what's going on. I'm going to draw a rectangular box. By the way, I do this is I draw two rectangles like this. I make them the same, and then just connect to the corners. Not the greatest drawing in the world, but it gives you an idea of the three-dimensional space here. Now, I know that rectangular boxes have a length, a width, and a height. Okay, so you might go, oh yeah, length, width, height. Okay, but that's three separate variables. The problem kind of gives me some information that can shrink this down to just two variables. Here's what it says. The base length is twice the width. So instead of using L and W, I'm just going to kind of delete that real quick. I know that the length equals twice the width. So I'm going to go ahead and call one of them x and call one of them 2x. Okay? So the length is twice the width. So doubling the width would equal the length. Okay? Doesn't really matter which one you call x, which one you call 2x. Okay? But we can figure this out that way. Okay, so now I've got it down to two variables. We have a rectangular box. Unless otherwise noted, assume that all 6 rectangles are on here. So the question next is, what is being optimized? What is being optimized in this problem? Well, for optimize, I look for either minimize or maximize. In this case, it's minimize. I want to minimize the amount of cardboard being used. Well, what we have to understand here is that the cardboard represents the surface area of this box. So what's being optimized here is the surface area. And what I want to do now is write an equation for the surface area of this box. Well, the surface area is just all 6 rectangles. Something to understand here is that in a box, there's 6 total rectangles, and every rectangle has a congruent rectangle on the other side, assuming it has all 6 sides. So I'm going to look at the base of this box first. What's the area of that base of the box? Well, that would be x times 2x, or 2x squared. But I have to remember there's a top that's also x times 2x. So 2x squared comes up twice. 2 times 2x squared is 4x squared. So I'll get 4x squared for my top and bottom. Now I have to figure out the 4 sides. Well, this side right here, if you follow my marker, this side right here has an area of xh, but there's another one on the opposite side of it that's also xh, so that gives me plus 2xh. Okay, this front panel right here, that has an area of 2xh with another 2xh on the back side. 2xh plus 2xh is 4xh. Okay? Again, I think this is kind of the trickiest part of the problem here, is writing these equations. But there we have it. I'm going to simplify that a little bit. I can see that these are like terms. So I'm going to write my surface area equation as 4x squared plus 6xh. Okay? That counts for all 6 sides of the box. 4x squared is the top and bottom. 6xh are the 4 sides. Okay. So now what I want to do is, the problem here is my equation has both an x and an h. So I want to get it down to a single variable. Now looking at this equation, I would like to get rid of the h here because I only have one single solitary h in my equation. Whereas subbing out the x's would be a little bit more complex because I have an x and I have an x squared. Okay. So again, how did we get rid of a variable in the last problem? Well, we used the constraint. The constraint in this problem is that we have a volume of 1,000 cubic inches. So I know that the volume of this box in equation form would be, length times width times height. Length times width times height. When I multiply those up, 2x times h is 2x squared h. And I know the volume must be 1,000. So I'm going to set 1,000 equal to 2x squared h. What I want to do now, since I want to get rid of h here, I'm going to solve for h here. To get h alone, I'm going to divide both sides by 2x squared. When I do this, I get h equals 500 over x squared. I'm going to box this because eventually I'm going to need to figure out the height, and I can do that then. So I'm going to rewrite my surface area now as 4x squared plus 6x. And instead of using h, I'm going to substitute in this right here as 500 over x squared. Okay. Now I'm going to do a little simplification here before I do my derivative. I know I'm going to do a derivative and set it equal to 0. 6 times 500, I know 6 times 5 is 30, so this would be 3,000. Okay? This x and one of the x's on bottom cancel to make 3,000 over x. In order to do my derivative, it makes more sense to write it like this. Okay, so here's my surface area in a single variable. Okay, now to figure out the critical point, where we have a min, I need to do the I need to do the derivative and set it equal to 0. Well, my derivative here would be 8x minus 3,000 x to the negative 2. I'm going to rewrite this in a way that's going to be easier to evaluate. I'm going to say 8x minus 3,000 over x squared equals 0. Right, I do my derivative, I set it equal to 0 to find the minimum here. What I'm going to do is I'm going to add my 3,000 over x squared to the other side. Now I want to group the x's together, so I'm going to times both sides by x squared. That gives me 8x cubed equals 3,000. Now I want to divide by 8. Here's where I'll use my calculator. 3,000 divided by 8. I get 375. So I know that x cubed must equal 375. To undo a cube, I'm going to do a cube root. And I get x approximately equals, I'm assuming this is going to be approximate. I got to do the cube root of 375. To do a cube root, hit the math button, and then number 4 is your cube root. And I'll go grab that 375. So I know that my x, right, which would be my width, is approximately 7.211. Okay, so that's one of my dimensions has now been solved. I have to find the other two dimensions. Well, knowing x, getting 2x will be quite easy. Now, just to make life easy for you, let's go ahead and store that answer as the letter x. So now I know 2x is 14.422. So again, this would be my width. My length would be approximately equal to 14.422. And then I need to figure out what my height approximately is. Well, I'll just go back to this height equation that I have right here. That's in terms of x. It's 500 over x squared. So I'll do 500 over x squared. And I figure out the height of this box is 9.615. Oh, sorry, these are all what, inches, I think? So those are my dimensions. The last thing I want to do is I want to know how much cardboard was used. Well, that would be my surface area. This time I'm going to use this surface area equation to calculate it. You don't have to. But since I have x already stored on my calculator, I'm going to type in 4x squared plus 3000x to the negative 1. Evaluate that. And I get the total amount of cardboard used would be 624.025. What was it again? 624.025. That's surface area, so it would be in square inches. Okay? Well, that's a way that we can make a box with a volume of 1,000 cubic inches with a length twice its width. We'd only use that much cardboard. Any other dimensions that make 1,000 and have a 2x1 base, we'll use more cardboard than that. That will be your minimum amount of cardboard used, right? A company might like that because you're using less materials, so the company will spend less money. All right, that's it for today. I'll see you guys tomorrow to work on some of these fun problems. Talk to you later. 2 Chainz.